proves the lemma. And now from the lemma we can easily conclude here. So for oriented random walk, what oriented random walk in dimension 4 and higher, it has this property which we call exponential intersection tails. And this was already noted and used by Kesten, Cox, and w.r.t 20 years ago. The point is that if you take two oriented paths and want to look at their intersections, intersections can only happen when they collide. They can only intersect at the same time. And if you look, so it's intersections of two oriented paths that correspond to the difference of the two oriented paths visiting 0. If we have two oriented paths in Z4, their difference is a random walk in a three-dimensional space because the difference is restricted to sum of the coordinates being equal to 0. But it's a random walk in three-dimensional space is still transient. So the difference between these two oriented walks is itself a transient walk in 3 dimensions. So it will escape to infinity, and the chance that it will reach 0 k times decays exponentially. Okay? For any transient walk, the chance it visits the origin k times is exponentially small. So we get the desired property, and that's why in dimension 4 we have the claimed behavior for oriented walk. So that completes part B here. For part C, we have to note two things. One is in dimension 2, any path, well, up to distance r, it will visit r points out of the r squared. So again, counting will tell you that you must have a singularity. For dimension at least 3, there is a measure, this path with exponential intersection tails, that has exactly this desired property. Okay, it's not so trivial to construct. So the first construction of these was in joint work with Tai Binyamini and Robin Pimentel. And then there are improved constructions by Hegstrom and Mossel. And anyway, there are measures in Z3 with this property. I should mention that independently of our work, and there was a related work by Candes and Zeytouni where they also used this path with exponential intersection tails in a similar context with Gaussian variables on the lattice. Okay, so I was hoping to have time to tell you the solution of the riddle, but I'm out of time, so you can enjoy the riddle some more, and thank you for your attention. Good morning. Thanks for waking up in this ungodly hour and coming here. So what I'll discuss today, is the subject of some work we did with Noam Berger some 6 years ago, and has remained semi-secret since then, although a few people like Ofer Zeytouni we've discussed it with. Anyway, this is so that's the main topic. But before going into that, since we're getting near the end of the conference, I want to tell you a kind of nice riddle, which I'll present the solution at the end, which is also about trail of random walker, but in a different setting. So this is a riddle that arose due to Arya Kantorovich. And he asked the following very simple question. Suppose consider a discrete time Markov chain on n states. Okay, can you bound the probability that at time t we visit a new state? So there is some state y, so that the hitting time tau y, this is the first time we visit y, equal t. And just can you, but the game is to bound this just as a function of n and t, so not relying on any parameters of the chain, no reversibility assumption, no degree assumption. And this function should, of course, go to 0 as t tends to infinity. So that was his challenge, find the best function of this type. And so I'll come back to this riddle later. If anyone has seen this riddle somewhere, please do let me know. Okay, well, I'll say that we'll actually n squared over t is the best up to constant function. Yes? Right, so we want, so tau y is the first time so that the chain visits y, right? The hitting time. So the question is, we want, for any Markov chain on n states, there is no other assumption that it's reversible or anything. We want to bound the probability that we get a surprise at time t that is after a very long time, so think of t as much larger than n, suddenly a new state that we've never seen before appears in the chain. And we want to bound the probability of that event happening exactly at time t. Now, we cannot bound the probability that it happens after time t, because the chain might want to stay at one state for a very long time and not leave that state. So there's no way to bound the probability that tau y is bigger than t. But the probability of having a surprise exactly at time t, that should go to 0, and it does go to 0. And the question is, how to do that. So it turns out, it wasn't clear in advance if it's a research question or a riddle. It turns out it's a riddle, but it's a fun one. So since we're near the end of the conference, I want to share it with you. Okay, any questions on the riddle? Okay, I should say that there's an example by Gadi Kozma and Offer showing that this kind of behavior is optimal, so you cannot get below this function. And they also already knew for graphs of bounded degree this kind of upper bound. But it turns out it holds in complete generality. Okay, so if you are somehow lose interest in the rest of the talk, you can solve the riddle. And so now let me start with the main topic. So somehow there are many flavors of a random walk interacting or viewing its environment or scenery, right? So the most famous is random walk in random environment, where the path of the walk is influenced by this environment. Then we have random walk in random scenery, where there is some scenery picked often at random, and the random walk is reporting to us what it sees, and then we try to reconstruct the scenery. And the flavor I will talk about today is a different flavor, where the random walk is moving in a maybe standard way, simple random walk or some other fixed random path that is not influenced by the environment, but it actually changes the environment. After the walk has traveled, we get to see the environment, not along the path, just the whole environment. And we have to decide, did the random walk actually go there or not? So let me be more specific. So here's an example, a general kind of example of the type problem. And we'll generalize it a bit. So we have so on ZD, okay, start with independent fair coins everywhere. So my coins are plus minus ones. So at every location, you have a fair coin. It's plus with probability half and minus with probability half. Okay, now all right. Consider a random walk path from the origin, and we'll consider several flavors. For instance, simple random walk is one example. A biased or oriented random walk is another, where in the oriented random walk, you just choose one of the d coordinates uniformly at random and increase that coordinate. Okay? So we have this path, and on the random walk path, replace the fair coins by coins that have probability q 1 minus q coins. So on the random walk path, let's call the random walk path S. Okay, this yields a law Q sub S for the scenery or the environment. So, and the average scenery we call Q. So Q is the integral of Qs deep C of S, where psi is the law of the random walk. And then the question is, can one distinguish, or for which dimensions can one distinguish between the original scenery, which I'll call P. So P is this. So I can call it mu to the ZD, where mu was this measure. And let's call nu to be this coin. So original scenery P and Q. Okay, so formally QS, you can think of nu to the S, mu to the ZD minus S. Right, so on the path, we put coins with distribution mu, with distribution nu, and off the path, we have the original distribution mu. And I'm thinking of the concrete case of fair coins versus biased coins, but of course, you can have any two measures here, mu and nu. They could be more involved measures. So mu is the original measure that we put on all the sites, and nu is the perturbed measure that we put on the path of the random walk. So I remember when Noam first told me the problem, he said, well, you know, a prisoner has escaped from the origin, and as he walked, in this case, a random walk path, kind of his path disturbed the environment, right? He walks and some leaves are moved away and so on. So there is some trace of his movement, but this trace is only stochastic. And he leaves a trace only along his path, which might be a thin part of space, right? So this is a prisoner with possibly with a d-dimensional helicopter. So he moved along, And along this path, which we don't know where the path is, he spread this bias, created this bias. And now we don't see the prisoner. We just see, from above, we see the environment. And the question is, can we detect that the prisoner has escaped or not? Okay, that is, can we distinguish this perturbed environment with a perturbation along a path that we don't know from the original environment? And we consider three flavors here. So simple random walk, oriented walk, and an arbitrary path. So in the third flavor, the prisoner is trying to choose his path. So a distribution on paths which will make it as hard as possible to detect him. But he cannot jump, so he has to go one side at a time. So it's a nearest neighbor path, but he gets to choose which measure on paths to use so as to decrease the chance of detection. Now, okay, so again, QS is the measure which has a S along and has nu along the path and mu away from the path. And of course, if we know what S is, it's very easy to distinguish the measure QS from P because we just go along the path and apply, count the frequency, look at the frequency of ones along the path and see if that frequency is Q or a half. So just using the law of large numbers, we can detect if we know the path. But the problem here is we're presented with the environment or with the scenery without knowing what the path is, and the question is, can we detect this? Right? Is the setup clear?
What is observable?
Observable is a sample from this measure Q. So, in other words, we have, so all we see is our pluses and minuses. Okay, so you don't know anything except seeing these minuses and pluses. Okay, but you know that the way they were constructed is from the origin there was some path, and along this path the pluses, you had the bias probability Q of plus, and off the path you had just fair coins, equally likely plus or minus. But what you see is just a sample from this. Okay, so you see pluses and minuses all over, and this pink path that I've now drawn, you don't see it.
But it's static. Is it static or?
It's not changing. No, it's picked once and for all. Okay, but it was picked randomly. We don't know the sample. We know the distribution of how it was picked, but all we see, this pink path we don't see. We just see these pluses and minuses, and the question is, do we have enough information to distinguish? So formally, we have two measures on plus minus 1 to the ZD, and are these measures absolutely continuous or singular? So there is a kind of 0-1 law which says in these cases that these are the possibilities. So either these laws are absolutely continuous to each other, or they're singular. So singular just means we can define some event, some collection of labelings, so that it has probability 1 for measure P, but probability 0 for measure Q. So this way we can distinguish. Question?
So the question is about exactly the absolute continuity, or is it, or maybe it's what I'm about to say is equivalent, but you flip the coin first to pick the top, and then the prisoner goes around and reflips the coin.
Yes.
According to the Q minus Q.
Yes.
And then you observe just, and the prisoner has walked already, and you observe just the pluses and minuses now.
Yes.
And can you tell if that happened, or if it was just the pluses and minuses?
Those are the same equivalent questions.
The same question, right?
Yes. Yes.
So does it matter in any sense how long the prisoner is walking?
Well, we are considering here the clean asymptotic variant where he's walked to infinity. Okay. So we want the path to be transient. So for simple random walk, we're going to consider it for D at least 3. Otherwise, there's no meaning. I mean, if the walk is recurrent, then well, of course, he's changed the whole environment. Okay. Yeah. So it's going to be a transient path, but 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 these two examples, he can go to infinity even in 2 dimensions. Let's rule out the one-dimensional case, not interesting here. Yes?
In the last example, the prisoner knows everything, and he chooses his path.
No. Good question. He doesn't see. He picks the law of the path in advance.
In advance.
Yes. Yes. Right. He knows the question, but he doesn't. He doesn't get to choose to look at the pluses and minuses and look and walk there. Okay, which I mean, you could argue you might want to look at that variant too, but yes. So yes, so consider that it's known, although okay, in many cases when you can distinguish, you can also reconstruct Q. So we'll come back to that. So you don't really have to know it. So, but to have a concrete question now, think of the parameter little q as known, and so we have 2 concrete measures to distinguish: either this capital Q built from the little q, or P. So, okay, so let's get some intuition for this question. So first, let's look at the large ball of radius r. In this, and let's first look at the simple random walk version. So in this ball, we have r to the d vertices, and about r squared of them are on the path S. Right? So this yields some intuition, which says, so for d less than 4, we expect a singularity. So right. Because certainly if you take d equals 3, you have r cubed points, and so of these inside the ball of radius r, right, constant r cubed. So we expect half of them to be plus, half to be minus, when it's an error of order r to the 3/2. But the walker is visiting r squared of these, so you'll get a perturbation which is larger than the standard deviation. So of course you can distinguish that. Right? So 3 dimensions is kind of trivial, and 4 is also still easy because the perturbation is large enough that it's distinguishable at the level of the standard deviation. So out of the r to the 4th points, we have r squared points perturbed. And so we're not sure. We see something which looks suspicious, but we're not sure. But we can see this at infinitely many scales, and we can make this scale separated enough so the information is essentially independent. So it's still easy to see that if you just, for separated sequence of r's, you get a perturbation where you have biased coins on r squared of the r to the 4th points. That's enough to distinguish. So because you have a shift which is a constant number of standard deviations at every r, and that's so if you see these two, right, you see this is the Gaussian distribution you expect, but you see one which is like that. So shifted just by, say, 1 standard deviation. That's something that you can be suspicious about. And formally, what you do is you look at the fraction of pluses in this ball, divide by the central limit normalization, so the square root of the volume, and then look at this at infinitely many scales and look at the average along these scales. So I'll write something more formal in this direction later, but basically this intuition is right, that certainly up to dimension 4, it's singular. What about dimension 5? Any guesses? Yes? The original P was a half. Okay. So in dimension 5, in the ball of radius r, there are r to the 5th points. And so the fluctuation we expect is, fluctuation we get is square root of that, while the walk only changes r squared points. So if we just do counting of plus minus ones, then we won't be able to detect the difference. However, it turns out, and people who know interlacements might have already guessed it, that in dimension, for this problem with simple random walk, in any dimension, the measures are singular. So go here. For simple random walk, the measures P and Q are singular for all D and for all choices of Q. So that's maybe part A. Now, what about oriented random walk? And actually, what I'm talking about, oriented walk, will work the same for any nearest neighbor biased walk. So any nearest neighbor walk that has non-zero mean. So what's going to happen then? Again, in a ball of radius r, we have r squared, r to the d points, but the oriented walk only samples r of them. Okay? So again, it's trivial that in dimension 2 we get singularity, but in fact for oriented random walk, we have singularity for d at most 3, while we have absolute continuity for d at least 4 and some q. Okay, so and here it's a little, why is the threshold between 3 and 4, not between 2 and 3? So notice that in R3, we have r cubed points in the radius r, but the walk only explores r of them. It's still detectable. Maybe you want to think why. I'll come back to that. But in dimension 4, it's already not detectable if the perturbation is small enough. So, okay, so for a large perturbation, but it could be detectable, but I cannot, there's a quantitative question for which I don't know if it can be still detected with coins. So it's certainly detectable if you allow more symbols instead of just 2, and the perturbation is large. But for coins, all I can say is that for small perturbation, it's not detectable. No. So okay. For q equals 1/2, right? The measure p and the measure q are the same. So.
So if you have a few samples of the environment, q is sufficiently large for it to be detectable.
Yes. Okay. And part C is for d equals 2 and q not equal to 1/2, p is singular to q for any psi. So psi is the law of the paths. So for any law on nearest neighbor paths, we get singularity in d equals 2. But for d greater equal 3, there is a q. If q is close enough to 1/2, then p will be equivalent to q for some psi. Okay, so this describes what happens in ZD, except for calculate. We don't know what is the threshold q where things go from. We have some bounds, but no precise theorem, yes.
When you say for some q not equal to 1/2, you mean for
Some,
the interval?
from the interval, yes.
So in particular, the oriented random walk satisfies the last.
Sorry?
So in particular, the oriented random walk satisfies the last statement.
No. So the oriented random walks, they will be singular for P for D at most 3. For D equals 3, they'll be singular, but there is another measure on paths. Those of you who were in the percolation workshop might remember which measure, which does give absolute continuity. Yes?
You say some C. What's the restriction here? You can't allow something like where you can step back and forth between the origin and
So thanks. Psi is a measure on transient paths, so measure on paths that go to infinity. Okay, the prisoner is actually trying to escape. Okay? Not going back and forth in the yard, yes. Okay, any other comments? All right, so,
One more question.
yes.
Not quite sure how to formulate it, but you would like to say you would like to be able to tell where the prisoner is, not just that there was one.
Well, you'd like to, but,
In the counting case, you can tell quite a lot about where the path is.
you can tell what?
In the counting case, you can tell quite a lot about where the path is, because you can lots of different balls.
Right. Okay, well, the proofs give you some information, yes. In fact, the proofs for i.i.d tell you, some locations where you know he was definitely there, some very localized areas. So not a specific site, but something of logarithmic size where you know he was there. Okay, so let me go to sketch the proofs. So for part A, it's it's a kind of intuition that we were happy to notice, but I think certainly many people here are aware of this, that the walk as it goes off to infinity, it is really different from percolation in several senses. And one is that the walk fills in abnormally large boxes. So here is the relevant proposition. Simple random walk in ZD, D greater than or equal to 3. A will for infinitely many n fill more than half of a cube of side log n to the power 1 over d minus 2 before reaching distance n from the origin. So the walk starts at the origin, and of course its path is much more tortured than what I've drawn. But along the path, right? So this picture is very far from being to scale. Along the path, there will be these boxes that are filled by the walk, or at least more than half filled, and these boxes are big. Okay, and this. So why is that going to do the trick for us? So you might want to think of a concrete D like D equals 5, and then we're saying there are boxes of side length cube root of log n that are half filled by the walk. So the point is these boxes have large volume. The volume is substantially larger than log n. Right? It's log n to the 5/3, or in general log n to the, where is the eraser? So this is just a fact about sample paths of simple random walk. And see, so these cubes have volume log n to the power d over d minus 2. Right? So much larger than log n. And the walker will perturb the distribution in these boxes very much. Because instead of being, these boxes are half filled by the walk. So suppose that Q was 3/4, then half the box has coins that are 3/4, and half the box has still the fair coins. So it means that the fraction of ones in the box is more than 5/8. Right? So this is a large deviation. So under the measure P, the chance of this for a specific box is e to the minus constant times the volume of the box, right? Because just Cramer theorem, Chernoff bound, whatever, large deviation for fair coins. If for some volume, the probability that a number of k fair coins came out, you toss them, and more than 5/8 came out heads, is exponentially small in this k, and the k here will be this, the volume of the box. Okay, so under P, this has this tiny chance, and of course, a priori, we don't know where this box is, but it's somewhere within this from the origin. So the number of choices for this box, so we just have to multiply by a constant n to the d in order to bound the probability this will happen in any box up to distance n, right? So under P, right, much smaller than 1 over n to the d. So even after you multiply by n to the d, this number is tiny. So under P, the probability of seeing any such box that is volume larger than log n with this kind of perturbation is extremely tiny. It won't happen under P, but I'm saying under Q it will happen. So that's how you can detect the singularity. Okay? And right, so any question? So finally, why is this fact about simple random walk true? This is just basically once you guess the right property, this is easy to prove, and there are various related results in the literature by Sinai, Mazel, Schlossman, and others about filling a box, and there's I think maybe there are refinements. I think there's Erwin. I think you have something related. I mean, I'm trying to recall. Right. And certainly there's, as I mentioned, there's something related coming up in interlacements, and so as I said, once you decide that this is the property you want to do, this kind of thing is well understood, because if you have a box of side R, you know that, let me draw it a little bigger. So you know that random walk, if it enters the box, it is, say if it enters the middle of the box, it's likely to fill R squared of the points. If we want to fill more than half, then we have to make R to the d minus 2 such trips. So each time, to get from the boundary of the box back to the center costs us some constant probability. So to do R to the d minus 2 excursions from the center of the box to the boundary of the box has probability e to the minus constant R to the d minus 2. And after R to the d minus 2 such trips, each trip captures r squared points. And it's not hard to see that when you combine all of these, you're going to get a constant fraction of the box. So there are many ways to make this precise, and it's not hard. Yes? Yes. Yes, and there are techniques to hunt down the constants, but I'm not getting into that at all. And so, so you get this probability, and then if you want to see which boxes will be hit, then as you go to distance n, you have about n different trials. So you want that this thing should be of order 1 over n or 1 over a power of n. And this tells you which radius r you can determine. You can find a box of this type. Because again, each time I reach a box, I can think of independent trial. Am I going to take this box and go back and forth r to the d minus 2 times? The chance of that happening is this. And so if I choose r of order a suitable constant times log n to the 1 over d minus 2, then this will indeed happen. Okay? So that's for part A. And that proves singularity for any dimension. Now, what about oriented random walk? So for d at most 3, we're going to do counting. And at first, it looks like counting won't succeed because, as we said, for oriented random walk, we have only r points within distance, within distance r. So r out of the r cubed. But if we look at it a little more closely, again, this is going to be easy. We're really not, so let's take d equals 3, oriented walk. The walk is not really exploring all of space. It's staying quite close to the diagonal. Right, so walk is mostly confined to the points close to the diagonal. So say if, so by this I mean that if the distance from, so the diagonal where all the coordinates are equal, the distance from that, and, okay, so what's the relevant point on the diagonal? Let's take the L1 norm of x, and just look at the vector which has the same L1 norm, so this vector, but then over, so we divide by 3. Right, so we want the distance from x to this relevant point in the diagonal should be less than a constant times the square root of the norm. So as the walk goes to infinity, just a simple consideration with variance tells you that when you get to the hyperplane distance n from the origin, so L1 distance n from the origin, the distance from the diagonal there will be typically about square root of n. So using that, we can just confine our attention to this. So fix some large constant c, and confine our attention to this subset of the space. How large is this set? So if we are going to look everything until distance r, then the number of points in this set will be order r squared now. Okay, so points so we can just bound it by points which go at most distance r along the diagonal and at most distance root r from the diagonal. So that gives us a size r squared if we are in 3 dimensions. And then from these r squared points, the walk has perturbed r of them. So it's, again, square root perturbation, which is noticeable at the central limit level. And because we can get these perturbations at infinitely many scales and the different scales are independent, it's easy to combine this to get singularity. So that's why in dimension 3 we get singularity. Okay. I said in this case, in dimension 4, so this was the counting argument, and we saw the counting argument was not sharp for simple random walk, but it turns out that this correct counting argument is sharp for the oriented or the biased walks. But to check that, one needs to prove absolute continuity. And here we use a technique that's been used several times before, in particular in joint work with Levin and Pimentel in Annals of Probability, and also in separate work of Bolthausen and Schnittmann. I'm going to misspell, sorry. So, and this is the idea of just to prove absolute continuity of density of 2 measures by bounding the L2 norm of a suitable density. So now we're going to, okay, so these are papers that concern different settings, but the technique we use here is the same as the technique used in these 2 papers. So we take D, which is, and again, these were in different settings. So let's take D equals 4 or greater or equal than 4. Okay, and the key lemma that will be useful both for this part and for part C is the following. So suppose that the probability that when we take, so I want to take the 2 independent copies of the path C, and then I want to take the intersection of a path S with another path S tilde, and I want this intersection to be bigger than K. Suppose that this probability is less than some e to the minus ck. Okay, then for Q, which is near 1/2, to be more precise, the 2 measures are absolutely continuous. Now, more precisely, the condition we want for Q to be near 1/2 is that if we take the measure nu with respect to the measure mu and do the L2 norm of that, so I square that and integrate d mu, this should be less than e to the c. This c. Okay, so I'm writing this is the condition in a general setting, and what this integral comes out in this special setting we're considering is just q squared plus 1 minus q squared, all of that multiplied by 2. Okay, so if q was 1/2, which of course is not the allowed value, then this product would just be 1. Right? So if q is near 1/2, then, right, then q squared plus 1 minus q squared is also near 1/2. And so multiplied by 2, it's near 1. So it's going to be less than e to the c. Right, so this c is some positive number here. What? Okay, so I had this in the original. So mu is the original background measure, and nu is the perturbed measure. So mu for us is fair coins, and nu is the biased coins. Okay? But this is the general statement. If we have a background measure and a perturbation measure, we have to look at the L2 norm. If this is less than this e to the c, where e to the c is the intersection parameter for the paths, then we get the absolute continuity. For all k. Or for all k large enough. Thank you. Okay. So and to prove that, so to prove this lemma, you just look inside a large box of size n and restrict everything to this box, and then it is to look at a if we take Pn with respect to Qn, so P and Q are just the same measures but restricted to this box. We want to take the Radon-Nikodym derivative. In any finite box, these measures are definitely absolutely continuous. We take this L2 norm. And the idea is that if this is uniformly bounded by some bound that doesn't depend on n, then the sequence of Radon-Nikodym derivatives, which is a standard martingale, will be a uniformly integrable martingale, and the limit will give us the density of P with respect to Q. So this is some standard fact about densities you can find in many places, including w.r.t.'s book or others. So you have to check this kind of thing, but in fact I'm going to do it the other way. So yeah, you need Qn with the way I wrote it, Qn with respect to Pn. So this will give the absolute continuity of Q with respect to P, and then some 0-1 law will give the equivalence. So now when you compute this density, or the L2 norm of this density, so you have to remember how is Q constructed. It's constructed by picking this path and averaging. So if gamma is the space of paths from the origin, we have to pick two paths. Outside we have, so outside we have this integral with respect to Pn. Inside I want to compute this density, and so to do that I have to average over these paths, and since I have a square, it corresponds to picking two paths. So I have deep C of S, deep C of S tilde. And then inside here we have QS of omega over, let me create more space here. So we have deep C of S, deep C of S tilde, dPn. Okay, here we have QS of omega, QS tilde of omega divided by Pn of omega taken twice. Okay, so So again, the path S and S tilde are chosen from the space gamma of paths going from the origin. Everything is truncated at distance n, so I'm not having all the notation here in the integral, but I hope it's clear what we're doing. Now, we want to compute this. Now, all right. So what's inside the integrand here can be written as a product over all paths, all vertices v inside this box of side n, and there you have just the product, and I'll write it in this form qs of omega at the point v, qs tilde of omega at the point v, divided by p of omega at the point v squared. Now, okay, so this is what this integral amounts to, because once I fix S and S tilde, the measures are just product measures. Okay, so now when we want to compute, we want to integrate this, all this product. So there are several types of vertices. So if the vertex v is not on the path S and not on S tilde, then of course this ratio is just 1. So we can restrict here to v, which are on at least one of the paths. But then you see if a v says on the path S but not on S tilde, then of these two factors, so it's good to actually think of this here one p and here another p. So of these two factors, if v is on S but it's not on S tilde, then this factor is 1. So we just get this factor, and this factor will integrate to 1 because we're integrating q over p with respect to p. So really the only thing that comes in are vertices that are in S intersecting S tilde, and there you get the L2 norm of nu over mu. So actually what you end up with is a nu over mu quantity squared, and we'll integrate that with respect to mu. And this is the number we call theta, I believe, over there. Okay, I didn't call it. Right, so this is this number. And we take this number to the power of the size of S and S tilde. Right, so we're taking some exponential moment here. So this is taken to the power S intersect S tilde. But if the tails of S intersect S tilde decay exponentially, then it will have a suitable exponential moment. So if this decays faster than e to the minus ck, then it means that if you take any number less than e to the c and take the moment of that, this will be convergent. So you get that this remains bounded. Okay? So that